Asia has experienced an unprecedented increase in the severity of flooding over the past decades. In 2020, more than 250,000 Vietnam households have been inundated and over 70% of the population is exposed to risks from flood-related hazards. The existing predictive models for the region rely on elevation-based geometrics and localized water gauging facilities that omit subsurface factors in rural communities. Western flood prediction systems have several data requirements and coupled layers that can back qualitative stipulations. However, the limited data-driven research, particularly in remote regions, calls for a different approach when analyzing Southeast Asian floods. That's why I wanted to investigate flood vulnerability from a novel and eccentric perspective, using percolation theory. Percolation theory deals with the properties of networks formed when sites are occupied with probability. In other words, it aims to describe the interconnectivity between nodes of a system. When the probability for a site to be filled in is equal to that of the critical probability, long-range connectivity appears. At this phase transition, percolation theory demonstrates a mathematical equivalence to flood accumulation and the properties of which water flows through the shortest pathway. The analogy between mechanisms of flood inundation and percolation theory may be proved to not be so fundamentally remote. Can a statistical reconstruction of geological and overland flood mechanisms applied in percolation theory predict the flood vulnerability of a region in Southeast Asia? First, I established the objectives that the model should achieve. I then researched which hydrological parameters are the most influential to Southeast Asian floods. I then determined the boundaries of my first study, the region of South Vietnam from 2000 to 2020. Step 1 was to batch download the necessary products from the NASA Earth Data Pool, and a program was written to streamline this process. The raw data was then pre-processed to extract the information in the desired file format, correct reference system, and filtered using quality assurance layers. Further data pre-processing was required for the Aster satellite products, such as the correction of depressions and flats. Using the digital elevation model and a generated flow direction grid, the slopes from the topographic gradient were calculated to delineate the watershed. Following this, algorithms applying percolation theory were programmed and tested on the area of interest. The algorithm first intakes the ND array outputted from step 2 and begins by defining L, the length of the matrix, N, number of simulations, and the infill, the threshold for inundation. First, the cells in the ND array that are not inundated are masked. From this, the inundation probability P was calculated, and spanning clusters were labeled using a union find algorithm. Then, the percolation probability for the given matrix L for n number of random inundation probabilities was generated and plotted. The percolation probability of P can then be extracted from this very graph with its corresponding x value. Overall, it was found that the percolation vulnerability of the Southeast Asian watersheds have increased over the past 2 decades. From the digital elevation model, lands that were represented to have the greatest inundation rates are the plains nested between mountain ranges, and the higher density of extracted stream networks in these plains were fascinatingly remarked. Because the mountain regions and some Southeast Asian regions are congregated proximately, the water volume of the branching streams converge and all contribute to inundating the same lowland basin. Compounded with a few tributaries evident, this demonstrates long periods of time before proper drainage, faster flood propagation accelerated by the slopes of nearby mountains, and massive runoff dangers. From the hydrologic soil group study, approximately half of the soil was found to be soil group C. Considering the amount of cells assigned a dual hydraulic soil group, a high antecedent moisture rate can be observed in Southeast Asia. It is inferred that this is caused by the presence of water tables, horticultural development such as rice paddies, or monsoon rainfall, all of which occupy a significant water absorption capacity of the soil, thus increasing the hydrological connectivity and thereby volume of flood water. And from the land cover, the average hydrologic condition of the area of interest was noted to experience a prominent increase. Intriguingly, the inundation probability of the area of interest enters a phase transition in 2016, reaching peak probability of the study duration only by 2017. This is likely as a consequence to increased urban development, where activities such as replacing vegetable ground with pavement largely increases the imperviousness of the land. There was a remarkable mathematical similitude observed between percolation theory and Southeast Asia flooding events. Strikingly, both systems exhibit a cubic root order when plotted and demonstrate features such as continuity, differentiation, spanning cluster density, and function turning points that can be then used to describe flood mechanisms such as flow accumulation, the abrupt phase transition in flash floods, flow propagation paths, and the turning point in flood magnitude. The application of percolation theory to model natural disasters induced by climate change and the use of recurrent neural networks to map flood magnitude were further investigated. A flood vulnerability index tool was also proposed to build flood-resilient Southeast Asian communities. This would enable community leaders to build and advocate for relevant and sustainable protection against floods in susceptible regions before disaster strikes. Some next steps for this project include converting the codebase into a Python open source library so that other researchers can explore applications of percolation theory and perform batch earth science analysis. Moreover, I would love to build an animated visualization of flood formations in a manipulative 3D environment through Autodesk Maya. Nevertheless, the remarkable case study of percolation and its affinity to flood mechanisms compel, for further investigation, countless applications in predicting Southeast Asian inundation and enabling systemic action towards progressive flood protection measures.